All right, good afternoon. Happy Friday. First Friday of the semester is here. And unfortunately, it's cold and we're not used to it yet. I feel like walking outside, I feel like a baby that's from the south now. Like 30 degrees, it's not that bad. Feels bad. We'll do a kind of like mixed virtual in person one more time at least, and probably switch back to kind of normal next week. The first thing I wanted to do is just really briefly touch on the in-class assignment. So if you have that done, get it out. If you don't have it done, get it out and furiously work on it while I'm talking. We're going to turn this in at the end of class. So as you leave, just set it up here on the front is fine. So in-class assignment. So in part, this is to get at least some appreciation of how difficult it is to use some sort of tool for flow visualization. Like in this case, he's basically putting chalk dust in a fluid, and it doesn't have to be exactly like mine. Everybody is furiously working. There, go away, stop. So in part, it's to say, like, it's not that easy to go from a visualization, like putting chalk dust in where you can see things moving, to be able to back out instantaneous velocity from that type of information. You can write computer code to be able to do that sometimes. If you can track like one particle, like pixel by pixel, like this particle moved to there, and this is how long it took. You can, this many frames per second, and this is how the distance it traveled. You can get velocity, not instantaneous velocity, but velocity at kind of a short span of time. But it's really difficult, especially if things are dynamic. So probably, the very first couple ones you watched a couple times and were like, I don't know, and just started to draw arrows. That's what I did. So I just kind of started drawing arrows. Is that exactly what the velocity profile looks like, especially, right, this one, like the really initial where things are really dynamic, it's probably super off because it's really difficult. Once we start to have the whole system kind of settle down though, so I'm looking kind of these three down here, then the velocity becomes much more straightforward to be able to say this is the instantaneous velocity at this time, because the velocity field is not changing with time in the same way. So it still is changing with time a little bit. We are still like gradually slowing down, but it's certainly not changing as fast. So that's going to be something that we're going to have to kind of appreciate about fluid flow. It's going to be really difficult to describe accurately. It's going to be difficult to model. It's going to be difficult to make equations for. It's going to be difficult to visualize when things are really dynamic and changing and mixing. It's going to be much more simple. Sometimes we're going to be able to exactly describe what's happening when things are at steady state. So it's going to be harder to do experiments, harder to visualize, harder to do everything when things are changing with time, because obviously it's going to be much easier at steady state. And one of the real kind of key takeaways from this, we have really three different tools that we talked about for flow visualization. We had timelines, path lines, and streak lines. Path lines and streak lines are the two kind of most common. So they're these top two here. A path line being, right, you follow the path that one individual particle takes, kind of like a long exposure. You're thinking like high, car headlights at night in like a long camera exposure, like watching where that one individual thing is going, or the route that a receiver ran in a football game. Streak line being like you're injecting dye or smoke or some sort of tracer continuously into a fluid flow and watching where that goes. Both of those things are useful in different contexts to actually visualize flow with an experiment. Both of them in steady state are the streamlines. So streamlines are things we'll talk more about today, but that's kind of one of the takeaways. When things are dynamic, all of these different flow visualizations are giving us different data. We're going to have to kind of sort that out. When things are steady state, they really all give us the streamline. So it doesn't really matter which one we do because it's giving us the same information. And ta-da, it's giving us the thing that we actually wanted in the first place, which is information about the velocity field. So that's kind of the takeaway, hopefully, from that. All right, so let's talk more about streamlines because they're going to be with us for a while. So we'll call this streamlines. All right, so what are streamlines? Remember, these are lines tangent to velocity field. They're tangent to the velocity field. Another way of saying exactly the same thing is the velocity perpendicular to streamline is exactly equal to 0. So if they're tangent, then there's no perpendicular component, saying the same thing. But kind of an important thing to note is they give us the shape, the direction of the velocity. They don't give us speed information. So speed can change along our streamline. All right, so let's draw a kind of simple picture, right? If we have, this is solid walls, and we have fluid flowing in this corner. Think of this as a two-dimensional picture, so it goes in and out of the page toward you and away from you. Our streamlines are going to look something like this, where they kind of bend into that corner, and the further away we get from the corner, kind of the less you really go down deep into the corner, right? Maybe that makes sense to you that that's the shape of the flow. We'll be able to describe this exactly a little bit later on, but we could draw these as the streamlines. And, something like this, far away, we're maybe going a little faster. Closer to the corner, our velocity vectors are a little bit smaller. So these are those are, as well as I can draw them at least, our velocity vectors. So the streamlines tangent to the velocity. So we can dust off some of our vector math, right? You all have put that away in a cupboard. It's got very dusty. We're going to dust it off a little bit. Okay, so what does it mean? How do we do, right, cross products and dot products and all those fun things with vectors? Do you remember all that fun stuff? So if we're saying a streamline and the velocity vector, if those are tangent, we can write, they're going to be, okay, let's draw it. So there's going to be, I don't know, a streamline like that. We're going to have a velocity vector at some location here. We'll call that v vector. We can define our streamline. Our streamline is going to be, I'll write it in a different color. We can define our streamline by, like, it's a really small vector, infinitely small, but pointed in the same direction, right? They're tangent, they're both pointing in the same direction. Our velocity vector, we described that by, right, the x component times I hat plus the y component times j hat plus the z component times k hat, UVW. We can do the same kind of thing, this really small chunk of streamline. Small chunk. It's a differential chunk of our streamline. ds, we can write that ds is going to be equal to the little tiny x part times the I component, the little tiny y part times the j component plus the little tiny z part pointed in the z direction. So that would be just a differential vector pointed in whichever arbitrary direction. Okay, these have to be pointed in the same direction. So like the relative magnitudes of all of these things have to be the same. So what does that mean? So that means like u compared to v has to be the same as dx compared to dy, right? Like the ratios have to be the same between all of those. So we could write an equation like that. So if we compare u to dx, that would have to be equal to that, right? Does that make sense? Like the relative ratio of these different components have to be the same. So if it's, you know, this big in y and this big in x, it has to be like that big in dy and that big in dx. Same for dz, w, dz. So this, we'll put a box around this. This is going to be an equation that now we can do stuff with. This we can call the differential equation for streamlines. And okay, why do we care? Why do we do this? Well, we're going to be able to use this to kind of calculate what the streamlines are from a velocity field. So we can look at like, this is the velocity field, this is where all the streamlines are, and go back and forth between these two different things. We could have also derived this equation from kind of more like vector math, right? If you want to say that you want to do vector math and say these two vectors are parallel or they're tangent, you would do the cross product and say that the cross product of these two vectors is 0. Right, so we could have done a cross product where you do like the fun things and you pick out different, you know, if you remember how to do that a little bit, you could be reminded how to do that. We could have done that and we could have gotten the same equation, but I think it's easier just to think they have to be kind of the same ratio of sizes. Okay, so this is going to let us go from descriptions of the velocity field, like as a vector, to descriptions of streamlines back and forth. Before we do too much of that, though, let's just take kind of a quick aside about velocity fields, because I think probably right now that's a little bit of an abstract concept. So what do we mean by that? What might they look like? What might be equations for like real velocity fields that we could run into? So this is kind of an aside. Velocity fields and flow dimensionality. So velocity fields are going to be really important for us because if we know the velocity field, we're going to be able to know anything that we would want to know about a flow. We're going to be able to know forces exerted by a flow. We're going to be able to know flow rates. We're going to be able to know friction that's happening in a flow. We're going to be able to know any question that you want to ask. We'll be able to answer it if we know the velocity field. So that's why we care about it. Oftentimes, we're not going to look at 3D pictures. You can. Typically, we're going to be dealing with things that are, right, I mean, really, you can be looking at like 4D things where you can have changes in X and Y and Z and time. That's going to be more complicated than we will ever try to get explicitly. Like, we're not going to do the math of that. We're going to do the math of like 1D and 2D things. Really focusing on 1D and kind of saying 2D, that's fun. We'll leave that to the mathematicians. 3D, certainly we'll leave it to mathematicians or a computer or something like that. But we will do some of the basics with like 1D and maybe a little bit of 2D stuff. So, all right, so 1D, typically, we'll look at 1D and 2D flows, just as kind of a note. All right, so what might that look like? So here's our first example. We briefly mentioned this previously, but if we imagine two different plates and there's flow in between them, where might this occur? This would occur in like a lubrication scheme if you have one part like sliding over another part and there's an oil or some sort of lubricant in between. Oftentimes you can simplify down like a shaft rotating in a like a rotor in a stator. If there's a lubricant in between, you can simplify it down to something that is sort of like this right there. Maybe they're round, but the gap is small. It's kind of like standing on the earth and saying, well, the earth is round, but it's pretty flat. We'll be able to do the same kind of simplification. So it's a flow that shows up fairly regularly. It would look, say, something like this if we drew, that's the worst axes. We drew axes, we'll give that Y, X, and Z. And we're going to have our parallel plates. So we'll have a top plate and a bottom plate. Let's imagine our top plate is moving with a speed of capital U. All right, our bottom plate is moving with 0 speed. So our bottom plate is stationary. The gap between our two plates, we'll call it B. And in between, this is where our fluid is. So our fluid is in the gap between those two things. So what would happen to our fluid flow? What would it look like? Again, we'll prove this later on in the semester when we actually are able to do the math and force balances and stuff to be able to figure this out. But what it's going to be is a linear change in velocity between being stuck because of the no-slip boundary condition at the bottom plate to being stuck because of the no-slip boundary condition at the top plate. So we have these two kind of pinned interfaces. So our velocity field is going to look, our fluid is going to be moving something like that, where it has a speed of capital U at the top plate, a speed of 0 at the bottom plate. We could write the equation. Again, I'm going to just magic this out of thin air, but we will actually be able to derive this and prove that this is true. It would be our velocity field. We could say capital U times Y over B I hat. So that would describe our velocity field, right? If you look at it, if Y is 0, we have a 0, so the whole thing is 0. If Y is equal to B, for at the other side, then Y over B is B over B, so that's 1, and we're going at capital U. And it's linear in Y, so this would describe that linear profile I drew. This, again, if we're trying to look at like kind of describing in words, this is describing a 1D flow, it is pointing in one dimension. That's less important than how many dimensions it's changing in. So we only have changes happening in the y dimension. So that's what we mean by 1D flow. So 1D flow, we see changes in the y dimension. Right, because we have a y variable, right? So that's the variable is telling us the dimension that we have changes in. The I hat is telling us it's pointing in x, but that's not really the important for flow dimensionality. It's how many different dimensions, x, y, z, and time do we have changes in, right? The dimensions we have changes in, that tells us about flow dimensionality, not which dimensions we're pointed in. So you could imagine like we would have a two-dimensional flow where, maybe it's instead of a infinite kind of two parallel plates, it's like a box. Then you might have like everything's still pointing in x, but you could have changes in y and in z. And we would have to consider both of those. So not to hammer that home too much, but which way are we pointing, which way are we changing are two different things. We're going to have to kind of try to separate that out. Okay, second example. This would be flow in a diverging channel. Or we'll do this. This is flow in a diverging pipe, I guess is how I have it driven. And this is the top one is a flow that's driven by the movement of the one plate. This is going to be a flow that's driven by pressure differences. So this is pressure driven. Again, this is really just taking examples that we'll see again later and giving you a little bit early so you have kind of a sense of where we might use these things, where we're going. So what would that look like? Let's draw a pipe. So there's my pipe. There's a straight section where it's constant diameter, and then we're going to look at the transition between that to all of a sudden a kind of a cone-shaped part where our diameter is expanding. For a system like this, we're going to use cylindrical coordinates because that's going to be easier than x, y, z. So we'll have still an x direction, which is down the pipe. We have an r direction, the radial direction, and we have an angle direction, a theta around the circle of the pipe. Right, so those are our cylindrical coordinates. We're going to be doing really only Cartesian and cylindrical, but we will do both coordinate systems. So again, dust off your vectors and all that fun stuff. We will have to do that a little bit for this class. All right, so what does the equation look like? What does the flow look like? What we will find, again, right now I'm just pulling this out of thin air. Eventually, this is a problem that you will be able to solve yourselves. Our flow is going to look like that. So again, the no slip boundary condition forces it to have zero velocity at the pipe walls because the velocities have to match and the pipe's not moving, so the fluid can't move. The maximum velocity is at the center. So usually we're going to describe put like our axes right at the dead center of the pipe and go out to the radius rather than like putting it at the bottom of the pipe or somewhere else. We'll put it right at the center. In this section here, right where our pipe diameter is not changing, in that section we have 1D flow. In this section, we're going to have 2D flow. For the 2D section, I won't write the equation. I'll write it for the 1D section, but I'll at least draw some pictures. right? So you can kind of imagine what's going to happen as we transition from the constant diameter to all of a sudden it's expanding. We're going to keep the same shape. So it's still going to be a parabola, but it's going to all slow down. So the max velocity is going to decrease as the pipe gets wider and wider. So we're going to have something maybe like that. And then further down, we're going to have something maybe like that. Right. And exactly how that works would depend on like the angle of divergence, how fast you're expanding, all that fun stuff. Okay, so right, this is 2D flow. We are changing in R and X. We are still only pointing in X. So it's still, the flow is all in the X direction, but it's two-dimensional because we have changes both as you go from the center of the pipe to the wall of the pipe. You also have changes as you go further down the diverging channel. So two-dimensional because not because of how many dimensions it's pointing in, because of where we have changes. Then this 1D section, we would have, I'll write the equation out of thin air. It would be something like this. The velocity is equal to some maximum velocity, 1 minus little r over big R squared I hat. Really what that's saying is it's a straight parabola, r squared, centered at 0. And it goes to 0 at the pipe walls at big R. So that's that equation, that's what that describes, just as a parabola. Again, you can see in that equation, it only depends on R. So that's the only variable of our things where we have changes. It's all pointing in X, but we're varying in R. That's why it's 1D. All right, so we're going to be able to describe different velocity fields. Simple velocity fields we'll be able to describe explicitly like this with equations. You can actually do, if you're really good at math, fairly complicated velocity fields that you can actually still describe explicitly. The more complicated it gets, the harder that is to do. But there are a lot of things that actually are possible to describe explicitly, even if they're maybe not possible for me or you. People can. Okay, so what can we do with this? So we can, if we know an equation like this, like I said, this gives us, if we can describe the velocity field with an equation, it's going to eventually give us a tool to be able to do kind of anything we want and say anything we want about how that fluid flow is going to behave. So we're going to take just a little bit of time to explore kind of a small piece of that with this idea of flow in a corner. So we drew that, right? This guy up here, right at the beginning, flow in a corner. So what is the velocity equation for that? So this is another one that's fairly straightforward to be able to actually write what the equation is. If you go back and look at it, right, you can see this is going to be two-dimensional. We're going to have changes both as you go up and down. Velocity is going to change. It will also change as you go left and right. So we're going to have changes in X and Y, and it's going to be pointing in X and Y. So this is going to be 2D and also pointing in 2 dimensions. All right, so what would this look like? Just for your own reference, because some of the math here is going to be important for your homework, and I'm going to go over it relatively quickly. The book goes over this exact same problem in example 2.1, so that might be a good place to like loop back on, especially as you're doing homework and trying to work through yourself. You'll have at least seen kind of the same thing twice. So what is our velocity field? So this is flow in a corner. This is A X I hat. Minus A Y J hat. So X and Y. X and Y are our position variables. So they're going to have units of things like meters or feet or inches or centimeters or something like that. So they're position things. These have units. In this particular thing, we'll say they have units of meters. And then A is going to be kind of the scaling to make all of the units play nice. So the velocity has to have units of like distance per time. So meters per second or feet per second or miles per hour or whatever your favorite velocity is. So A has to have units as a scaling thing that tells us about the speed. And it's going to have units of something that makes the units work out. So if X has units of meters and we want the whole thing to have meters per second, then A has to have units of per second. So we'll say A in this case equals 0.3 per second. Okay, we can answer different questions. So what's the velocity at some given location? I don't know, let's find it out. So at point, say 1, 3. What's the velocity? Well, let's plug in those coordinates and see what happens. So we would have something like this. V equals 0.3 per second times our X position, which is 1 meter. That's in the I direction, minus 0.3 per second times our Y position. So we could write the velocity at that point is 0.3 meters per second I hat minus 0.9 meters per second J hat. Right, so what is that? Just to draw a quick picture, what is that looking like? So something like that, we're looking at, this point here, 1, and this point 3. So if we looked at our velocity right there, it's going to be something like that. Right, where this equation is describing that particular vector, the velocity vector at that location. So it can tell us, if we know the velocity field equation, we can tell the velocity anywhere we want to in our fluid. Okay, what else can we do? We very first today in class looked at this equation for streamlines. So we can use that to be able to say, this is our velocity field. What are the streamlines going to be? So let's see exactly how that would work. So we can look at this and determine streamlines. This is going to feel a little weird. I guess kind of the nature of it. But once you do it a couple times, you'll get the hang of exactly how this works. So we can just write down our differential equation for streamlines. That would be u over dx equals v over dy equals w over dz. Okay, the very first thing that we can do is say, are any of these 0? We say, aha, w is 0, right? There was no point, it wasn't pointing in that direction. So we're only pointing in x and y. I'll maybe let's write it like this, I hat and j hat. So it's going to get confusing a little bit. Like, are we talking about which ways are we pointing, or the dimensionality of it? Which ways are we changing? In this particular case, we're looking at like w is 0, which is the part pointing in z. So you'll have to be a little careful on that. Then we have a differential equation to solve. So we have u over dx equals v over dy. We know what u and v are. These are the parts pointing in x and the part pointing in y. So let's throw those into our equation and see what happens. So this would be ax over dx equals minus ay over dy. Right. Okay, so now how to solve a differential equation like that? Probably not a form that you guys are super used to solving. It's fairly straightforward, right? So a differential equation, all you have to do, treat dx and dy just like a thing until it's time to integrate to actually get a number. So what we're going to do is get, instead of 1 over dx and a 1 over dy, let's shift things around to other sides of the equation so that dx is not 1 over dx, it's just dx. So we can write, this would be 1 over a times x dx equals minus 1 over a times y dy. Okay, we can now multiply both sides by a. So let's take this whole thing and multiply it by a. And we get 1 over x dx equals minus 1 over y dy. Then we can integrate both sides. Our goal is going to be to get like a y equals equation, because we could then plot that. We can plot y equals something. We can plot it, and that will show us our streamlines. That's going to be the goal. So let's integrate so that we can get a y equals equation. So we're going to integrate that side, integrate that side. What is the integral of 1 over x? Okay. So that is the natural log of x.
Plus c.
Yes, wonderful. Plus, we'll call it c1. What is the integral of 1 over y? So it's going to be a negative, same thing, right? ln of y plus c2. Okay, we want to get this to like a y equals type form, so it's going to take a little bit of work to be able to do that. Okay, so let's just, for instance, we'll put the x and the y on the same side and see if we remember any algebra tricks. This equals negative c2 minus c1. We play our signs right, but those are just constants, so one constant, negative minus another negative, like, I don't know, let's call it just one constant. It's still a constant. So we'll smush these together. We'll call it C instead of C1 and C2. We'll just call it C. All right, now how do we, any ideas of how to get rid of the natural logs? So if you do that, we can't quite do it yet. What happens, how do you simplify, if you have two logs that are being added, how do they simplify? Yeah, Sam?
So you do the way in the next one.
Right, so they, if you have two, like natural log of x plus the natural log of y, that is equal to the natural log of x times y, right? And if you have like natural log of x minus the natural log of y, remember this from like high school? It's been a long time, right? So these are all the fun things that you have to try to reteach yourself a little bit. So this is the, not an h, the natural log of x, y equals c. Now we can take this and rate e to the power of both sides. So now we can say e to the natural log of x, y equals e to the c. Okay, and now it simplifies to x times y equals e to the c. E to a constant is still a constant. It's just a different constant. So let's call it a new, let's call it c still, because I'm running out of numbers. Call that c. Maybe you want to call one c3, and then one can be just normal c. Maybe we should do that. Let's call this c3. So then it's clear we're actually like switching, and this is a new constant, still a constant. All right. Almost there. So let's get this into y equals form. So this would be y equals c over x. So this is our equation. Our equation for streamlines. Why might you think it has an unknown constant still left over in there? Or what might that look like? If you think back to, say, like this picture of what the flow looks like, where I've drawn the streamlines. So that unknown constant is still left over because each, right, I've drawn 3 different lines. Each of those 3 lines has its own personal value of c. So it's like one is c equals 1, c equals 2, and c equals 3. And you plot those and you get those 3 curves. So the streamlines, they're going to be an infinite number of them to describe the flow. And each one is going to be unique because it has its own constant. So when we find streamlines, we're always going to have this unknown constant hanging around. And that constant is there to be able to give us multiple different lines to like fully describe the flow. Yeah, no.
Is this like the equation that we found only applicable like in the case of corner, or is it? Like
It is.
General equation? This
is the particular equation is just is the streamlines for this particular flow. So this would be flow. It's flow in a corner. Turns out it's actually also flow against like a flat plate because they're the same. Just kind of, you know, one is just half of like the other one is both sides of it basically. But yeah, it's only for this flow. So if you wanted to do the streamlines for flow, say like in this diverging channel, it's going to be an entirely different equation. We would use the same process. You would start with, this same equation for streamlines, and you'd use the same process to be able to figure it out. But each time you have a different velocity field, you have to go through this to find what are the streamlines. But basically, if we have this velocity field information, then we can go from that to like a visualization type tool. We're going to use streamlines for more than just visualization eventually. So it will get us to that as well. Again, it'll be a tool. We'll be able to use it for looking at flow rates and some other things like that too. Okay. Last thing that we will like just really briefly get started on. No, we won't get started on it today because it's going to take us more than the 4 minutes that we have to even get started on it. So what we have going on for Monday. So today is our very first homework. Will be right after this. I'll make it live on Moodle. It's going to be doing some of these kinds of things. The very first thing that you should do though, and I think it's labeled as problem 1. There's a link to a video about flow visualization. The video is like, I think maybe 20 or 30 minutes long maybe. I ask that you watch the first like 13-ish minutes kind of before you actually start the homework. It's kind of a fun video. The video series, we'll watch a number of them from this series throughout the semester. They're videos that were made like in the 50s. There was a National Science Foundation grant basically to a number of different universities. So they were people that like experts in the field at MIT and places like that studying fluids, and they got a whole bunch of money to make flow visualization and stuff across like a wide variety of different topics. So they're still some of the best videos. It's kind of fun because everything is super analog because it's the 50s. So there will be things that you look at like that feel like they're computer animations and none of it is computer animated, which makes it kind of fun. So that's the first thing. Watch that. Hopefully everybody is able to access that fairly easily. I think the link that I put is a YouTube link, so hopefully it works. They also have like a home on a separate website, but that doesn't always work for everybody. So make sure you watch the video. It's only like 13 minutes. It'll be kind of fun. It will try to give you a little bit better picture of like what are streamlines and streak lines and path lines and what are different tools, and you can actually see as they're talking about it. So it should be kind of a good thing. And then you'll do some equations and calculations like we did to find streamlines. The very last problem, you're going to find equations for streamlines like this, and then you're going to plot it. There's an example like picture that's going to be there of kind of a formatted plot. I ask that you format it better than like default Excel when you're putting that and turning that in. So take time to actually like have axes labeled and make it so that it doesn't look like you'd like selected your data, hit insert chart, and turn that in instantly. So spend a little bit of time on that. There's an example that you can kind of follow the formatting. That's due next week, Friday. The in-class thing set up at the front as you leave, and have a good first weekend. Good job on the first week of class.
Yeah, you're good. Okay.